what's the gorge you guys have to get over? How many feet?
500 feet wide by 50 feet tall.
How deep is it?
50 feet.
So it's, you could put columns in if you wanted to, or you could just go all the way across in one shot. Depends on what bridge type you need. So new model, chips and feed. We'll go to, this is just a starting point. For any of the bridges you're designing, you could probably go here for a 2D frame. So you guys can help me. What number of stories for this? It will be 1. Number of bays, it will be 3, right? And then we have different heights. It's probably best to start with the, I don't care, we'll do 25 and then I'll add 10 to this one. So they'll both be 25 initially. And then the width is probably best to start with the 150 and then I can do those 40 feet. Are we okay? All right. So I'll get rid of this one, especially because I'm not interested in the out of plane motion. So I click that off so I only see one picture. Now I go to view, click on show grid if you don't want to see all those ones and B's, C's, and D's. Turn that off. Zoom in a little bit. Start rolling my mouse. And then obviously here we don't have columns, so right away I can just circle, grab that one and that one. It doesn't matter if I grab joints as well. It won't delete joints that are part of another number. But hit delete and then those are gone. We want to see the nodes. So if we view, set display options, turn off invisible. Now we can see the nodes. The lengths aren't right yet. Let's do that before we create the sections. This length is 150. So what I'll do is, so they don't have some kind of mirror image, then I could do both of these at the same time. One moving to the right 40, one moving to the left 40, but I don't know how to tell it to do both at the same time. So I have to do one at a time. So select edit, move, and move in 40 in the X direction, that joint. And then this one will do the exact same thing, you move it to the minus 40. I can see it a little more. So we have to move this one down by 10. So I click on that joint or circle it. It says down here 1 point selected. Edit, move, and make sure that it's showing still what I typed in before. So you got to zero that one out, and then on Z put minus 10. Okay, so at least all the lengths should be right. So that's about how fast it is to create a model. The geometry. So you can right click and check. That's my preferred way. Go to location and it says that was 110. Right click on this one and the location is 150. So far so good. And this one says 110. This column here is 35 feet. And then the next one should be 25 feet. Okay, so that's good. Obviously, this is there's no reaction here. That's a long cantilever, so we need to do something about it. We need to make that a roller. So now you can grab this joint and this one. So down here it says 2 points selected, and say assign joint restraints. And what we're going to do is restrain. The X is what we don't want to restrain because it's a roller. We want it to be able to move in the X direction. Otherwise, it won't feel the earthquake at all. We want the Y later. The Y is going in and out of the page. We want to restrain that. And the Z is vertical and sitting on something, so we want to restrain that. The Y, and then, so that's fine. Rotation about the X. I want to restrain. I don't want it to turn. Rotation about the 2. I don't want to restrain. That's around the Y. So it should be able to rotate. And then about the Z, and it needs to be restrained. So when we say OK to this, we should get the right icons which indicate rollers. We have a fixed condition here. So click on this joint. sections. So we're in feet units right now. Define section frame. Add new property. If you just leave it as steel, it doesn't. I don't like how this version does this, but if you go to concrete, it has some solid sections. So let's go to tube first. We're using. I'll just assume that this material property is fine. It's a 4,000 psi concrete. If you have different concrete, you can create your own material or copy that material, modify it as needed, modify the body's elasticity. So here I'll put SUP for superstructure for the bridge itself. And then we want to change the depth to be 6 feet. The overall width is 40 feet for this section. Flange thickness is 1 foot, and the web is 2. So top and bottom are 1, the sides are 2, the overall width is 40, and the depth is 6. That's this section here, right? It's superstructure. So we say OK. So don't forget, after you create these sections, to assign them to frame members. It's easy to create sections and forget to assign them, so it's just has the default. So now say add new property, rectangular. This is for, we'll call a column, COL. And then, so you have to be careful which one's which direction. In the 2 direction, I think that's our longer one, that's 6 feet. And we can verify this in the depth is 4. That's the wrong way. Put it 6 and 4 this way. Okay. Because I know moment 3.3 will be the moment in this direction. And looking at this, this is, oh, I was right the first time. 4 versus 6. Okay. So that is correct. So it's the weak direction in this direction. Okay, that's called column. And again, it's using the 4,000 psi concrete. Now you want to assign it, so I can just highlight around this. And right now we only have 3 members. We're going to split it up into 4 members. So let's say assign, frame, section. So I'm going to select superstructure. So now it says SUP for all those. And then for the columns, grab those and say assign, frame, sections, column. Now if we wanted to define a different material property, you go define materials. Here's the 4,000 psi. So you can look at it and look at the Montes elasticity. Remember, this is kips per square foot, not KSI. So you could get out, it says you could do it in units, I usually do it here. But kips in inches here. Define materials, let's go back. And there's the 3,605 KSI, that's the Montes elasticity that's found from 57,000 is the square root of 4,000. That's what that number is. So if you had a 5,000 KSI or PSI concrete, you could find a new number and put it in here, or you could copy this. You could click on add copy of material and call it whatever you want, and then change these numbers. And then when you go back to the section, when you go here, define frame section, let's say column, modify, you just select, you would select the new material you created. You have to create it first. It would just be the Montes elasticity you would have to change, nothing else. In the way we're using it. Okay, let's add some additional load. Or should we, let's split, maybe split, see what I told myself to do. Okay, let's split these up into moments. So 3 frames are selected, the superstructure ones. You say edit, edit lines, divide frame. And you say number of frames, and each one will be the same length, because the ratio of the last to first is 1. So each one will be 10. made up of a bunch of members that are interconnected. Columns, we're going to split into, what do we say, 5? Edit lines, divide, and just say 5. Leave that ratio as 1. Okay, so you can go in and look at them all, right? And then I click this, because we don't want to see that. If you click this icon, it gets rid of the designation, section designation. So we have a lot of members now, and what else do we do? Let's add some load and mass. We want to add, you tell me, how much I'm going to add so many kips per foot along the top as add a dead load. How much? How many kips per foot? Two point four. 2.4 kips per foot. Because 35 pounds per square foot multiplied by 40 is 1,400, but that's pounds per foot along the line, right? And divide that by 1,000 to get it into consistent units, so that's 1.4 kips per foot. And I said also add 1.4, and 1 kip per foot along the line with 2 barriers, a half a kip per foot each. So that's, we want to use 2.4, right? So I'm going to grab all of these, make sure you don't accidentally grab the column ones, zoom in, okay. And also it tells me here 30 frame members selected, so that should be good. Each one's 10. So I didn't accidentally grab the columns. I want to put that on there. And then say assign frame, frame loads down here. I'll go to distributed. It's going to put it in a dead load case, which is okay. It's add a dead load. We're going to include that. Gravity is the direction, so I don't have to put a negative. And then we just put 2.4 in, right? Our 2.4 is kips per foot, and we're in kips and feet units, right? So it's showing it being applied there. And I'll click on this, and I don't want to see that. Let's add the mass also. And that's for dynamic considerations. It affects the periods. Affects the dynamic response to your structure, so that added mass is there. So let's put that on there. So we'll select again. We're going to distribute it. It's 30 frames selected. Say assign. Now you don't go down to frame loads, just go to assign frame. And then over here, you go to see align mass. We're not lumping the masses in each node. It will do that automatically for us based on what we do. And then this mass should be 2.4 kips per foot divided by 32.2 feet per second squared, divided by gravity. That gives us the mass per foot. So that's 0.0745. Okay. So that shows it. Let's save it as something. Let's add the weight and mass of the bent cap. That turned out to be handy important. It's solid, it's not hollow. And let's see, how much should we add? Well, we already have this cross section going all the way to the intersection, right? So we don't need to add the total weight like that. We need to add the weight of this hole. And the mass associated with it. So let's say it goes 6 inches on either side of the column. The column is 4 feet this way. So it's this multiplied by 5 feet. So what is that? Actually, that's quite a lot. Probably pretty heavy. And it'll be, we'll put it on a node rather than distribute it. We'll put it at the top node. Is that clear what I'm doing?
No, actually, could you please explain? I was just wanted to ask, what is it you're calculating?
A solid bent cap. Remember how where the column reinforcement comes up, it's not hollow, the bridge, it will be solid.
Oh, okay.
So I'm adding the weight that's not in there right now based on the cross section we gave. Yeah.
When you did the frame line mass, did you do the add to existing or did you do the replace? I missed
It didn't matter because we hadn't given it any.
Okay.
So either one. Okay, and so it's 40 minus 4, so it's 36 feet. This is 6 minus 2, so it times 4 feet. And then the length, the column in this direction is 4 feet, but the bent cap will be another 6 inches on either side, so multiply that by 5. So that's 720. Multiply that by, it's 150 pounds per cubic foot concrete, and we use 0.15, so this is already in kips. So that's 108 kips that we'll put on it. And we'll do it at both locations, right there and there. Let's say assign joint loads, forces, and dead. Says replace existing loads. I guess it's okay, we didn't apply any joint loads yet, so it doesn't matter. So you have to think when you do this, because you could be erasing, you could do things separately and adding them. Force in the X, force, okay, force in the Z. So now this one doesn't say gravity direction, it says force in the Z, so you have to put a negative unless you wanted to pull up on the string. So it's minus 108. There it is, that's good. And I want to click onto those same two joints and add the mass associated with that. So you say, so we're seeing different things here, adding loads and masses to members as well as to individual joints. Then I say assign joint masses, and yeah, it's in all three directions. Let's see. I do need it in the one direction and three, the two direction. If I'm just looking at in-plane behavior, it doesn't matter. I don't need it, so I can leave that at 0. And I'm going to take the 108 kips, divide that by 32.2. So it'll be 3.35. There, and there's a 3. If you want to do it in all three, that wouldn't hurt it. Okay. Save it. Let's run this and see, and we're going to do some more things to it, of course, but let's just do this at the start. You can see that it's going to run the defaults. It'll have dead load and modal analysis, and the modal will tell us the periods of destruction and load shapes, and that's important to earthquake response. So run now. This is the dead load. Let's go look here. Just under all the self-weight and the added dead load, we have the maximum space is about 0.1 something feet, so that's just over an inch of vertical. So that's reasonable. It's not 20 feet or something. You know you've made a mistake or you have a bad design or something. But an inch of displacement and 150%, that's not a problem at all. And that inch wouldn't be there because when you build it, you build cameras. So you do this calculation, and then you flip this diagram upside down, and you give that to the contractor, and they'll build that in the opposite direction. So under self-weight, it will just come down to the profile. Otherwise, you bounce across these stands. Okay, now let's look at the modal displacements. So you click on, you go to here where it shows displacements, and you go from dead, change to modal. And then it says mode 1, you can pick the other ones. Mode 1 is the longest period. That's in this direction. There. On yours, when you're running it, you'll have animation. Somehow I've lost that. We worked on that large 30-story building and it didn't like it, so I don't have the ability to animate but I know what it would look like. It just goes back and forth like this, the mode shapes. So this is mode 1. It's over 1 second, which is it under there? How about if I go all the way to the goes do that? Move this one. first one is just, this is 1 second, so it's just onto this. So it's pretty low. It's lower than the peak ground acceleration. So the ground acceleration is 0.7 G, and we're way down to 0.3 on the first period. I mean, that's the dominant period. It doesn't mean the displacements are small, but the accelerations aren't that large. So under maximum credible earthquake or maximum considered earthquake, the structure acceleration is only 0.3 G, when the ground is hitting 0.7 G. It's a de-amplification rather than resonance. It's like an anti-resonance. It's actually reducing the accelerations. Whereas if in the modes in this region, or if mode 1 was here, it would be amplified by two or 3 times. Okay, but that's mode 1. And mode 2, look at that. That's this type of display shape. That's the second mode. It's 0.45 seconds. So that's way up here. So the second mode will have very large amplification, the largest possible based on our ARS chosen ARS group. Mode 3. Now mode 3 you can't see, and that's because it's probably going in and out of the page. If we rotate this, you would see that. Let's see. Maybe 3D. I can rotate it. Yeah, so it's moving horizontally. We didn't restrain that. So one of the things I wanted to do, I want to get, at least in my work here, I want to get rid of the mode shapes that go in and out of the page. We're not looking at that. So let's unlock it. Let's view it. Set 3D view. I'll change this back to 0. And we'll look at it in the X and Z direction like that. So it's directly on sideways. And then what I'm going to do is, I don't want to mess with these one of the restraints we've already played with and we're happy with. But all of these other nodes, I want to restrain only to move within the plane. So I'll grab them like this, and then I'll go in and grab these ones as well. So every single one, I'm going to do it all at the same time. Say assign, joint constraints. And I don't want to restrain the X, so turn that off. I do want to restrain the Y that's out of plane. The Z, I want it to be able to go up and down. It's in the span, it should be able to go. It's not just horizontal, it should go up and down. Rotation about the X I want to restrain. If it's acting in the plane, that shouldn't be occurring in the rotation about the Z. The rotation about Y I don't want to. So it's triangular X marks for this type of restraint. Okay. And then they're little symbols, which are kind of annoying, but they serve the purpose. So now let's run it again, and you'll see that those other mode shapes are gone. It's only all the mode shapes are the ones we're interested in. So mode, that's mode 3. Let's go back to mode 1. Okay, so the same mode, 1.07 seconds. It's primarily deformation of the columns and some maybe of the bridge superstructure. Mode 2 is 0.45 seconds as before. Mode 3 now, we don't get that mode out of plane, we restrain it, so it's all behaving this way. All these modes we've seen here would also be in the other one, but we've eliminated any modes that are not important to our project. So all of the, in an earthquake, all of these modes are going on, some greater, some lesser, depending on the excitation, depending on the actual earthquake that comes in. Okay, now that we have the mode shapes, let's unlock it, which throws away all the results. You have to unlock it to make a change to the model. Now we're going to add the spectral plot, and then look at those results, and then go from there. So you say define, functions, and then the function is a response spectrum function. And here is where, when we get the actual motion that we post, you could say, let's see, from a file, and then you've saved it, and it says where, you go find it, and then you apply it. We don't have a file, we're going to create it, so we go down here, user, and then add new function. And then you can call it whatever you want, function 1 is probably fine. So at 0, it's 0, add, that's at 0 period, that's here, we're at 0 acceleration, and I'm doing it in G like this, and then we'll have to scale it by 32.2 to get it into real acceleration, 8 per second. 2. At 1 second, it's 0.3. And let's just put 1 and 2 seconds. So it knows where to go to continue. It'll continue that line, the last line. Is this right?
Yeah.
This is a 2. Okay. Now what we do is we want to run the analysis and define. Load case, add new load case. And then over here we're going to do a response spectrum analysis. And then this says CQC as complete quadratic. Complete quadratic completion. No, I don't know what it is. Actually, I don't remember. SRSS is, do you guys remember that? Some roots square no, say it.
Square root some of the squares?
Yeah. Square root some of the squares, I think that's right. Okay, so you got that one. Give me what this is, CQC. Complete quadratic solution. It's the Greek writing for solution. But my point is, don't click on that, put SRSS. And so we go to acceleration in the one direction, which is U1 is the X direction, that's the direction I want. Wherever my bridge is hiding now, under there, it's in that direction. And it's function 1, right? That's what we just created. Scale factor, this is where we want 32.2. I won't, because it was in G, I wanted it feet per second squared. Say add. Okay. And then this is important. Damping, if we're doing linear elastic analysis, which is what this is, use 5% damping. If we're doing nonlinear analysis for concrete, I would, in anything, I'd recommend 2% damping on the modes. So if you get to the point in your project where you're running nonlinear time history, don't use 5% damping. It's too much. Because the hysteretic damping is already providing that 5%. So you'd be using it twice, essentially. The reason that in linear elastic analysis people use 5% damping for structures is because they're not modeling all the energy taken out of the system by the hysteretic plastic engines. Okay, but so this says constant for all modes, 5%, so that's fine, looks good. And we'll say okay. Any questions so far? Everything's clear? Run analysis. And now you could have called it whatever you want. The default said A case 1, I didn't change it. So it's the response spectrum linear elastic analysis. And then say run now. That's just a modal response, so I'm not interested in that now. We've already looked at the mode shapes. Let's go to A case 1. This is the display shape. Right. It's interesting because it's taking squares from different modes, adding them and taking the square root. What happens is certain things end up looking funny. It's kind of hard to see here, but you can see that the superstructure constant looks like a kink and then it goes like that, right? Rather than continuous. And that's because any response from an individual mode will look continuous. What it's doing is that some root, some squared, or whatever, it's taking the displacements from all of them, squaring them, adding them, taking the square root. And because of that, you lose that nice continuity. So if we amplified it more, it would be hard to see because of this would be amplified too, but it goes like that. We'll often see that. You see the same kind of thing here. But if we looked at the response from any one mode, it would have a nice continuous look. From time history analysis, you won't see that. You'll see the superstructure continuing like this and not having a kink. You don't actually have a kink. So these are just maximum absolutes. So let's say you click on this one. Let's go to this joint here. And we have a maximum look at the moments. That's under dead load. This is the spectral, so moment 3 is what you're interested in. Those are the results. And for the same reason, rather than the moment diagram continuing through like this, like you would expect normally, where it goes through 0, it's positive and positive for the same reason. Squaring, adding, and taking square root, so it can only give positive, they can't give negatives. So if I right-click on this, you can see that it goes up to 21,000 kip feet. And then if we go, now remember, this is broken into 5 elements, 5 members. So if I right-click here, I'm only looking at that central part from here to here. I have to actually go up to this member, click on it, and then the top is about 19,000, 20,000 kip feet. Now that's 20,000 kip feet. When you're designing your columns, you don't design for that, right? You divide it by a Z-factor. This one here, pinned at the bottom, and has a different stiffness because it's a different length. If we right-click at the top there, it turns out it's similar, 19,000 something kip feet, and that's just coincidence, or maybe a good design. But there definitely is a big difference in transverse stiffness. One's approximately 12 EI over LQ, the other was 3. But then one's pinned and one's fixed. So, no, I mean, that's a different length, and then when those two things come into play, it turns out that the moments at the top are approximately the same. So similar overall lateral stiffness. Because it's an L cubed and they're different lengths. So actually that wouldn't be a bad design. So let's keep going. Now let's try to run an earthquake. Let's try one other thing first. We didn't run, let's add dead load to it. So let's say define, load combination, add new combo 1. So A case, response spectrum, scale factor, I'll say add, and this is a linear add, and then dead load. Linear static scale factor 1. You can scale these different amounts if you're looking at load factor design and you're multiplying things to get ultimate moments. So I'd say add. So in this case, it's just going to add. It's going to add the spectral results we just got and the dead load. So, okay. So I'll rerun this before we do the time history analysis. So that's just A case 1. But now let's go to combo 1, moment 3, for example. So now you've seen the moment diagrams are plotted upside down, so you can go to options if you want to plot it the way I normally plot it. And click on this and it switches the way the moment diagrams are plotted. I'm not sure what all these colors are, but let's go here to the bottom. And so now you can see the moment is 20,550, something 50. So I changed the moment in the columns a little bit. Of course, it changes the moment in the superstructure quite a bit because that's all the dead load is occurring. Added to the other things. Okay, define. Function, let's bring an earthquake in now. Time history. So this is a function, just like response spectrum, we didn't create a function, but this has thousands of data points, so we're not going to type that in. We're going to bring it in as a file. So say from file, add use function. So I have to browse for it. I'll call it EQ. EQ1. Browse, and then it's wherever you store it. I'll give it to you on Blackboard. to see why it's wrong. Okay, so first of all, we didn't tell it to skip this word, so it's reading that. That's probably the problem right there. And also, it's not .005, it's every 0.01 seconds. So that's 2 bits of information. While we're here, let's go down to the bottom and see, okay, so 61 seconds at 0.01. So here you say number of header lines to skip. It said 0, so it should say 1. And here it has time and function values rather than just one column of data. And now display graph. That looks better, right? We go out here. This is about 61 seconds. And this is in, if we look at view file, it's in G. So we're going to have to amplify this or magnify by 32.2 as well, or scale it, I should say. Okay. So it's called EQ1. I'm just moving across and looking at the numbers down here to make sure that it really looks like G values. 0.3, 0.2, so that looks reasonable. So it's an earthquake with a lot of motion. See that? It's not just like one big motion and then nothing. It's for 60 seconds, it's got a lot of motion. So let's say, okay, let's see what this can do for our structure. Now what we're going to do is say define load case. So just like response spectrum, we have a new load case, add new load case, and right now we're going to do time history analysis. We can do modal. If you're doing linear, you can do modal. If you do non-linear, I don't recommend that. We'll try both modal and direct, and we'll see you get basically the same results. Load is an acceleration. It's in the one direction. Earthquake, 1. Scale factor is 32.2. This will be, I want an output at 0.01 seconds at each time. How many increments? 61 seconds, so 6,100, right? 6,100. Because we're doing modal, we can just say constant 0.05. So this is comparable to the spectral plot. And linear elastic, it's going to do time history, but it's going to use a modal analysis to determine time history. So it's not going to be doing the squares of each maximum from the motion and adding to the square root. It's going to actually do the time history from each mode and add all those results together using a modal analysis. So it should give almost identical results to the direct integration. Let's call it time history linear elastic. Then from there. Okay. So we'll run everything. So it's running. It's done. So it's pretty fast using the modal approach. And then, let's see. Let's click this. Probably, you could click through here and go to time history and start at time 0, and then you could click. And then you could click like this, but it's changing the amplification. But it would take 6,000 clicks to look at it all. So there are different ways to look at it. When I was clicking through, it looked like it suddenly jerked, and what it's doing is the scale factor. Look at that, it's huge scale factor. So it's automatically changing it. So rather than continually moving like this, it suddenly jerks or it goes. It looks like it's going back when it's not. You could set this to a number, but it's so large, it's such a small motion that the ground is just starting to move right now. So perhaps a better way to see what it's doing, you can create a video of it and then actually watch it run. So that's a good way to do it. The other way is to click a node. Let's say this right here. I'll right-click that one, and that's node number 4. And then we can display the results over time for that node. So display, show plot functions, define plot functions, and then go to joints, add is the displacement over time. So this is more, right? We're getting almost a foot of displacement. You can see 0.8 or so. That spectral was only 0.2 something. So we're getting from this earthquake, we're getting, this is a maximum, considered a maximum pedal earth. It's a larger earthquake. It's actually one of the earthquakes I'm using on my 30-story building. So it's, it's why my building is 5.5 feet. Now you see why. But let's see, yeah, it's about 0.8. So anyway, this is the displacement over time. If you want to look window in on something of interest, let's say between 18 and 30, you can go back to here and say 18, 30. And so you can get a better feeling for the response over time. Okay, let's look at the acceleration. Let's look at that one. Show plot function, so I'll get rid of this one and bring in 4.1. And it says here acceleration. This is just in that zoomed in window, but you can see that it's interesting. It's not 2G, but it is above 1G. 1G is 32.2 feet per second squared, and we're getting 40 something this way.
Is it relative or absolute?
Yeah, that's a good question. I wasn't sure. It says relative, and what we're really interested in, what he's saying is when you go to define for joints, and we put in joint 4, I kind of hesitated, but you can click on acceleration. And for displacement, that is what he wants, relative between the ground and the top. But for acceleration, this is that, and then this is absolute. Really, we're interested in absolute acceleration. That's what that spectral, that's what this is. It's the absolute acceleration. It's the mass times the absolute acceleration of the force, not the relative acceleration. So let's try this and see what we got. Yeah, see, it's still about 30. That's the absolute acceleration, so that's interesting. We're getting more displacement, but less acceleration. Well, I guess not. When we looked at the spectral plot, the first load was here, which would be 0.3, and we're above, that's 0.3 G, we're above 1. Well, we're at about 1 G in absolute acceleration. So it is higher, above acceleration and displacement. Now what? Okay, let's unlock this, and then go define, load case. I'm going back to this, and then I'm going to change it to direct integration, but still leave a linear elastic. And there's one other thing we want to do. When you run, this is good for nonlinear analysis. It won't matter so much here because you could just combine it. But for nonlinear analysis, the dead load has to be on there before it goes nonlinear. Otherwise, it'll go nonlinear at the wrong time. The moments the actual force, everything else is really on this column plastic hinges. So what you do is you say, load pattern, dead load. You don't want earthquake. You want, otherwise you would be applying the dead load with the waveform of the earthquake. So you have to be careful. The ramp, time history, and scale factor is just 1, and then say add. So we'll go back and look at ramp time history, and then the earthquake is occurring as well. And then we're going to do a direct integration. Say okay. Let's go back and define functions, time history. What was it, ramp?
Right.
Okay, modify. Okay, that's what I want. So it's applying the vertical, the self-weight over 1. It's like having it sitting on false work, and you strike the false work, you remove the false work over 1 second, and now the dead load's on there. We're starting the earthquake at the same time. So then it just stays constant. After 1 second, it stays 1. But if you go back to load cases, the earthquake is starting at time 0, and the weight is starting at time 0. But after 1 second, the earthquake hasn't done anything. It's really small, so it doesn't matter. You could, if you wanted to be technically correct, is take the whole earthquake record and shift it to the right by 1 second. So have it start after 1 second, in other words. So that you put a dead load on for the first second and then the earthquake. But the earthquake, nothing much happens in the first second. So it's fine to do it this way. As long as by the time the nonlinear events are occurring, all the dead load, moment shears, and axial loads are on the structure in the right place, then it's correct. analysis, you no longer can say, I want all my modes to be 5% damped or 2%. You have to do it some other way. You have to do the damping because there aren't any more modes. It's not using the mode shapes now. So it can't help you with that. So, but you still want to remove, there's still damping going on. So what you say, I would click on specify damping by period. What was the longest period? About 1 second, right? So I would make this a little bit larger, 1.25. The bottom one I keep at 0.1. And we'll say 0.05. It's not in percentage, it's actual damping. Like that.
Is it using constant damping or like?
It's a combined stiffness mass, really. So it drops down in between and then goes up. And in the middle it's a little less, and then on the outside it's a little up. So by putting bounds on the period at 1.25 and 0.1, and then you'll probably only want to use periods that are less than 0.1 so that you don't dampen out the behavior of the system and take energy out of the system. Well, actually we're not using the mode, so that I take back what I just said. So this should be fine. So this will take a little longer because it's direct integration versus using the mode shapes. You can see us running.
Is it a real earthquake?
Yeah. This was given to me by Geotech for the project that I'm working on, so it's there are 14 different earthquake motions. I don't know off the top of my head which one this one is. Now I think about it, I think it was generated from a real earthquake, but then modified to give different frequency content and all that. But like I said, I didn't generate this or develop it. It was by Geotechs that are working on the project. You could go and look, see what it is while this is running. Let's see what it looks like. I think I have it. This computer. So it says 7 time histories, but there are actually 14. This particular one is this one. Let's see if this tells us that. Not a lot of information there. It's called, I changed the name to that. It's spectrally matched time series, but it's a maximum credible earthquake Koshiro. That tells you anything. That's the particular one that we're looking at. But it does say spectrum matching. So what happens is they take a real earthquake and then they modify the frequency content and the amplitude so that it more closely matches some spectrum that we're interested in, some high level. So that explains why it's so large, such large motions back and forth over a long time, rather than just 1 or 2 big spikes. In other words, it's probably more damage to the structure than would actually occur in one earthquake, representing a bunch of different possible limits. Okay, we're halfway there. So we won't get to nonlinear today. We'll keep on and try to, what is today?
Wednesday the
So
1st.
hopefully by Monday we've got the issue. I'm still working with those guys. We've got the issue resolved, and so we can all go over Monday. And if not, I'll go over nonlinear here and then just do it as you can. Wait till it's done before you do it.
Can you do the calculator band?
We have 2 minutes. What?
Band count mass? Can you do it again?
Oh, I just took the weight, the added weight of the concrete. Where is it? Oh, I think it's under here. Just the weight of the concrete here.
A comp.
Look like a I have a few time history floating out there, so. I'm pretty sure us deciding to do. I'm missing something because of the amount of time is just way up on. You ever do either of those? One instead of. They were kind of awesome. Maybe. So, something. One of the load applications somewhere there. Then I got no.
It's not saying
Don't think it makes much of a difference.
Oh, okay, gotcha. So we have to make like a mini suspension.
I'm gonna do.
I'm just gonna make a bridge.
We're trying to cancel its broadcast.
What?
My bridge is.
Yeah. So when we model it, though, we model all the way to here, right?
Look at the thing
So
that I
this
posted.
cross section here, in the analysis, goes all the way to there.
Yeah.
So what I did was, but
It's
you
pretty
want
much
to
what you're saying.
capture
It's like,
this extra, this weight, but you want to subtract out what's already there. So what I did was I just I added this, going out 6 inches on both sides of this column. Right? So you end up with solid, this is 5 feet, yeah? 'Cause this was 4 feet here. This is 5 feet, and then this distance here is this, which is 36 feet between this point and this. What else? And then the height from here to here is 4 feet. So I just said 36 feet by 4 feet by 5 feet. That's the solid concrete that we weren't including. Multiplied by 0.15 pitch per cubic foot. And that gave me a lump weight. That was the weight, and then I divided that by 32.2 to make that mass. And you have to, in SAP, you have to add the weight and the mass separate of that. It doesn't, if you add the weight, it doesn't add the mass. Prove that to yourself, do a little while. Is that clear?
The big gap only extends 6 inches.
Well,
on the sides of the column.
in my design, typically, you don't have to go much. If they finish, so they'll be, look at something. Okay. let's see
I
what
was
we can
curious.
do.
I was curious what was up there, bro.
So it should just
Let me do
have the plot results.
Let me do my thing.
Let's look at this. This is the, so you can see the
That's
results
90%.
look the same if you save them plotted on top of each other. They're probably like 99.9% same time history trade. So it's the same response. Of course, I would recommend highly when you do nonlinear to do direct integration. So it's good to go there. You can see here what we added to the dead load, put that on there, and then we ran the time history. All we have to do now is make it nonlinear. So on Monday, either way, if we're here or in the lab, that's what we'll be doing. And adding nonlinear features and discussing. Any questions? So start your projects, right? Sure. It's due when? On the day of the final.